Hey, hi, how are you? So recently I was messing around with a balloon. I blew up a balloon and I let it go. And I like kind of observed the way that it flew around and how it seemed like totally random. And I was trying to figure out, like could I make some kind of deterministic equation, or even just like what are the factors that change how a balloon flies? And while I was playing around with this, my dad came in and he said, "You can't determine that. That's a chaotic system." And boy, did this lead me down a rabbit hole. So today I want to go over kind of like what chaos theory is, some of the things I learned. First of all, big credit to Veritasium. He made a great video about this, about chaos theory, and some of like, there's really beautiful images and math behind the way that this works. So I want to give a quick overview of what a chaotic system is, what a deterministic system is, some of the main math behind these ideas, and then we'll do a little coding simulation. We'll code it up and we'll make some nice art and maybe make a computer background. So let's get into it. Okay, so there's this mathematician in the 1960s. His name was Edward Lorenz, and he was trying to create equations to deterministically figure out what the weather was going to look like in the future. So what is a deterministic equation? What is a chaotic equation? So a deterministic equation is like any of like the Newtonian like high school physics. So like if you have this ball and you throw it from here, like how far will it go? And so if you change like the initial velocity or the initial position that you threw the ball from, the position at the end will not be drastically different. It's deterministic and it is non-chaotic, being that that's the core difference. A chaotic system is one where when you change that initial position, the final state drastically changes. And then deterministic is, can you mathematically figure out where the object will be, or the system will be at the end of some given amount of time. So Newtonian physics, deterministic and non-chaotic. The system we're going to talk about today, the Lorenz system and Lorenz attractors, are deterministic but chaotic. So that means you can, if you know the exact initial position, you can figure out what the final position will be, but a tiny change in the initial position drastically changes the end position, and it ends up creating some really beautiful math. So the equations I have written behind me are some of the simplified equations that Lorenz came out with as he realized from his weather simulations that he had stumbled upon chaotic deterministic equations. And so these are going to be the backbone for our simulation and for the art that we're going to make. Okay, so I just wanted to start out by giving a little bit of a clearer look at these equations. So it's these three equations here. It's the three velocity equations. So the velocity of x is sigma times y minus x. This is the velocity of y. This is the velocity of z. So what we'll do is we'll take these equations. We'll set our sigma, rho, and beta constant. And with those constants, then we'll integrate the equations, find an x, y, and z value, and then use Python to plot that. So this is kind of what we're shooting for, some of these cool patterns where it ends up making this really beautiful art. Okay, so what we're going to do first is open up a terminal. Okay, and then we are going to start up a Jupyter notebook. Highly recommend you get this software. Okay, so we're making a Python 3 notebook. Call it cool. Okay, So first, we got a couple packages we need to install. So we need NumPy, we need matplotlib, we need SciPy to integrate, and we need that. Okay, cool. So import these packages. So now we need to create some kind of function. Okay, no, actually first let's define our constants. So kind of the classical constants that are used for a Lorenz system are 10 for sigma, beta is 8/3, and rho is 28. Okay, so rho we'll set as 28, sigma as 10, beta as 8/3, and then we'll need to set our initial position vector, our initial position state. So we'll just set it at 1, 0, 1, 0. And then we need to set some number of iterations that this will happen, and we'll need this upper bound for later. Okay, cool. So we have these initial constants, we have our initial state, we have the number of iterations this is going to happen, and then we have our upper bound, which will be helpful for our integration later. Okay, so now we're going to define a function, our function, which takes in some initial state and some time. That's not how Python works. Okay, and so in this, we'll unpack our initial state, and then we'll return our functions. So the initial function was sigma times y minus x, sigma times y minus x. Then we need to return x times rho minus c minus y, rho minus c minus y, and then we need to return xy minus beta z. X times y minus beta times z. Cool. Alright. So now this function returns our derivatives. So these are these main derivatives from the Lorenz system, right? So now we need to integrate this. And so we're going to use the odeint integration function from SciPy. But as part of that, we need some time array to integrate over. So our time is just going to be a NumPy array from 0 to our upper bound. And so our upper bound is just here for 4,000 iterations, it'll be 399. Our upper bound will be 40. Okay. And then we need to go to 0.0. Okay. So then we'll integrate. So these are our states. And that'll integrate the f function with initial state 0. Sorry, this should be state 0. Initial state 0 over the interval t. Okay, so then we can unpack our states, which will be 0, 1, and Okay, so now these x, y, and z are our position arrays of the integrated, right? So this is our x, y, and z initial x, y, and z position as it changes over the time, and then it's just integrated from those equations. Cool. All right. So let's just now go ahead and plot these. So we'll need to say we'll make our figure. We'll make our axes. And we'll say it's a 3D projection. Okay. And now we can just do plot our x, y, and z. And then we'll draw the plot, and then we'll show it. Okay, so let's run it. Oops, spelled something wrong here. Okay, problem was, gotta have a capital D here. Put a capital D there, x 3D. Okay, so we run that. Then now we got our constants. We define our function. Let's see. Right, so then we make our figure. We set up our axes here. So yep. Okay, so now I believe we can just go plot x, y, z, and then we can draw it, and then we can show it. Oh man, look at that. Oh my god. So cool. Alright. Nice. Very cool. Okay, yeah. So now what I want to do real quick is I want to create a second state. Oops. We'll go call it second state 0. And this is just because it'll give us a nice kind of view of how different and how wild this system is. So what we can do now is we can say states 2 we'll integrate second state 0 pass in t. Right, so we're integrating over the time interval t. Integrate the function f with initial state, second state 0. Good, and it's the same t because it's the same number of iterations and such. Okay, and so then we can do x2 equals states 2 0. Same thing for y. Same thing for z. Cool. All right. So now we can plot z2, and we'll go. I believe that's how that works. If we run this, second state 0 is not defined. Oops. Run this, run this, run this. You can see our red is different. You can see it starts exactly the same right here, like right there. They start in the, maybe if we make this a little bit bigger. I believe if you go DPI, god damn it, 1200. Then that ought to make this a little bit bigger for us. Okay, yeah, much better, much better. So you can see they start at exactly the same point, and they're pretty similar. but then once they kind of get into here, they really start to separate. And it's easier to see on an actual simulation when they're actually moving, but they start to separate, and you can see they're now widely like different. And these two lines don't necessarily correlate. So it's just a very interesting kind of system. And this is not the most convincing diagram, but I promise you that these lines don't correlate with each other in the same way. So let's go ahead and get rid of our x2, y2 second states. That was just a little demonstration. And let's make some nice art now. Because I don't know about you, but I really believe that this is really quite beautiful. So one thing that I think that can make this a lot better is if this was to kind of change colors as the time increased. So as we went further and further, have it change colors. So to do that, we have to we'll make a new cell here, and we have to create what we're gonna basically the general idea of what we're doing is we're taking a coloring array, and we're taking our graph, splitting it into a bunch of different segments, coloring each of those segments slightly differently based off some uniform change in a coloring array, and then plotting that graph. So first we need to we'll create a color changer, which will just be a numpy array from 0 to 1. So okay, so here in the numpy plot, it takes in a color, and it takes in a tuple. So that's like, but each of the values is between 0 and 1. And so this linspace function from numpy creates like an evenly spaced array from 0 to 1. And we know we want it to be size of x. And while I was playing around with it, I figured that if you square it, it works out better. Why is this here? Good. Okay, so we can then print this, and you'll get a better idea of what this looks like. So it's an array from exactly 0 to exactly 1, and it goes through that. And if we print, I think it's like this. Our size is 4001. Okay. Good. All right. So we have this color changer array. So now what we need to do is split up our graph into segments. So we need that, we don't need these two anymore. Okay, so now we'll set our segment length. We'll just go with 10 for now, but you can feel free to play around with this, and it's kind of cool. We need to iterate from -s to s. These are just so this is iterating by the segment length from 0 to the number of iterations minus 1 segment length. Cool. So we should have 400 technically different segments, I believe. So then we get our specific number from the color changer array, and then we plot it. So then we need to plot our x, I to I plus s plus 1. We need to plot our y. We plot our z. Good. And so, okay, so then we can pass in our color, and so the color for this specific segment, personally I found it to look really nice when you just have this color mine array, or color mine value changing the green of the segment. Okay, so this should now go from green to blue. Cool. And then plot.draw, plot.show. Okay, nice. If we run this, oops, this isn't gonna work. Oh, it did. Nice, look at that, man. It goes, so it starts green, and it kind of goes through here, and you can start to see like, oh, look, it starts to become slightly more aqua. And as it goes through, and it ends about here, that's the bluest spot. And you can really start to see this nice transformation. And man, that is beautiful. So then you can kind of do some cool messing around with like the colors. So like say we can make this one go by the square. So red and sorry, this was the blue value that we were changing. So this is now the green value we're making go by the square of color mine. So let's see how this looks. Oh, it's kind of cool. So it starts black and it ends up being like this aqua color at the end. That's pretty wild. So I highly recommend that you go through and change, mess around with these colors. And then also you can mess around with these values here, the rho, sigma, and beta, like from the Lorenz equations. So there's some cool ones here on the Wikipedia page, like let's see. So this is the one we did, 2810.3. And they also go through some of the math here, like if your rho is less than 1, then there's an equilibrium point, which is at the order. So let's try 1310 8/3. So 13, run that, run that, run that, boom. Look at that. Isn't that wild? Dude, that's so cool. Anyways, I eat this shit up. Okay, so, but let's take it back to 2010 8/3 because I think that's just like the classy one that's just clean. So, oops, why did that work? Run through them all one more time. Look at that. All right. I really like this one. I think it's cool. I think it's a nice colorway. So I want to set this as my background now. So to go about doing that, we'll need to, first I like to turn the axes off because I think they kind of interfere. And then let's go ahead and save the figure. We'll call it PNG format. Lock in the format as PNG, and then we'll set it to transparent true so that we can set a nice background for it when we finish it up. Okay, so this is kind of going to be what our background looks like. And if we go to, let's see, desktop, there it is. So there's our PNG, and you can see I've already gone through and done this and set my background to this. So check that out, man. Come on. Isn't that so cool? So you can go into system preferences, you can go to desktop and screensaver, and then you can go to it, and then it lets you pick a nice little background color for it. And then boom. You have a super cool background. You now know the math behind it. And there's really nothing cooler than that, I would have to say. All right, boom. So cool. Hope you guys enjoyed this video. Go check out the source code down in the description, or it'll be a pinned comment. It's a nice little GitHub link. And feel free to make pull requests or change the code in, and if you make something cool, let me know. Put it in the comments below. So thanks for watching. Hope you enjoyed this video, and I will see you next time.